once you've got time numbered, we're going to take our delta D, our centimeters, and we're going to use that to calculate velocity. Because, as we should know, the average velocity over any time period, ADG, is equal to delta D, that's the change in distance, divided by delta T, the change in time. So over the short distance of 1/10 of a second, our average velocity during that 1/10 of a second is going to be the distance we covered, 0.7, divided by the time that it took, 0.1. So when we divide 0.7 by 0.1, what do we get? When we divide by 1/10, honors class, what do we do? We just move the decimal point over by 1. So we're going to move the decimal point over by 1 for each of these. Okay? So this becomes 7.0, 16.0, 21.0, 27.0. Actually, we can leave off the 0.0, really. We'll keep two significant figures. I'll keep it on that one, and then we'll go on and just do it like this. So we have 52, 63, 72, 84. Okay, so we just divide by 1/10, and it's the same as moving the decimal place over 1 to the right. So this should be pretty quick. So I'm going to show you part of the old video for the graphing, and I'm going to pause it when I get to the significant areas of change. Here is...
This video is to walk through how to graph the velocity in your bus lab. So you're going to need the same two colored pens or pencils that you use for your displacement graph. And it will be helpful if you have your displacement graph as just a really quick reference, and I'll show you why. And we want to make sure that our axes line up pretty closely on the two graphs so that when you compare them, you are looking at it pretty close. So all I'm going to do here is just kind of make sure that my new graph has my x-axis in roughly the same position. I'm starting with this edge. I'm going to make that my 0, and then I'm going to count, same as we did before, whatever your highest time code is, minus 1.3. So that's going to be 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1.0, 1.1, 1.2, and 1.3. So you can see that on my displacement graph.
So that x-axis, the time axis, should be identical on both graphs because they're measuring the same thing.
Straight edge. After you've marked out where your line is going to be, where your axis is going to be. Another axis in. Go ahead and number the lines as well. 3, 4. And label your axis. Time and seconds. Time, seconds. Always put a label on your axis. Always put units on your axis as well. And now we're going to, again, take your straight edge. And right along here, you're going to draw in your y-axis.
Now your straight edge doesn't have to be a ruler. It could be anything straight. Use the corner of your ID or something. But if you don't have straight lines, you're losing points. You can't calculate slopes and stuff from wobbly lines.
Now we're going to scale it. So remember how to scale. look at your velocities. Find the highest velocity out of either column. In this case, for me, it's going to be 80.0. Yours will probably be different. Go ahead and circle that so you remember which number you're working with. Then you're going to count how many lines you have available on your y-axis. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I only have 11 on this graph. So I'm going to take my calculator, and I'm going to do 80. That's my highest value.
Remember to look at both of your tables.
7.872727. So remember, we always round up when you're scaling the graph, so I'm going to round this up to 8. And on my y-axis here, I'm going to count by 8. So 8, 24, 14, 6, 4, 2, now you're going to plot your data. Remember to use, again, the same 2 colors that you used before. Mark it somehow. Again, I've got mine written in a color, but you can also shade in your headers. I'm going to do red for that first one, and purple for the second one. You can do whatever colors you like, as long as it's 2 different colors, so you know which line on your graph goes with which data set. So
you should use the same colors that you used
I know
before.
that you can't see all of the blue lines on my graph paper, but that's okay. You'll still be able to tell what it is that I'm doing. So again, you're looking at time and velocity. Time, velocity, time, velocity. Make sure you're only graphing time and velocity. Alright, once you have your points drawn, again, I'm going to see lines on my graph paper.
Okay, I'm going to pause it here. So when we're done with doing our graph, we're going to do a best fit line. So our best fit line, which should actually be in the same color. Let me, since you did purple, I think I've got a purple sitting here somewhere. Yeah. So when we do our best fit line, remember that we should have about as many points above as below. This best fit line better be drawn with a straight edge because we have to get a slope from this. We have to get a slope from this. Now, notice that the best fit line that I drew did not go to 0. And there's a reason for that. Okay, pay attention. It probably will not go to 0, 0, and that's okay. There's a reason. Let's take a look and see what that reason is. So first of all, I'm going to get a slope. We know that slope is equal to rise over run. The rise is in centimeters per second. That's the change in velocity. Centimeters per second divided by the change in time, that's equal to acceleration. That's acceleration. All right? Now, when I'm doing this, let's say that I find that there's a good spot to get my slope right here.
I'm just making this up. Pretend like there are some blue lines that we can see. And I found a good spot right here. And let's say I found a good spot right here. So my slope right here, my rise over my run, I'm going to go on and calculate that. So that's going to be equal to 64 centimeters per second minus 32 centimeters per second divided by, what is that, 7.5 seconds minus 3.5 seconds. I'm going to put that in parentheses so I don't screw up my calculations when I put it in the calculator. Then, let's see, 64 minus 32 is 32 centimeters per second divided by 0.4 seconds. And that's going to be equal to, 80 centimeters per second squared. Okay? So that's the slope of this line. So what does that mean? What's the equation that you guys learned in algebra for a line? Oh, slope-intercept form. Yeah, there you go. Y equals mx plus b. So I have a b right here. Let's call that at about 4 of whatever those units are, which happen to be centimeters per second. Centimeters per second is a velocity. So that's got to be a velocity. The y-axis, this entire y-axis is a velocity. So let's call this velocity is equal to, well, I just said that the slope of the line, change in velocity over change in time, is acceleration. So that's acceleration. And x, in this case, x is my time unit, and this is some other velocity. This looks really familiar. And if you look on page 14, your equation sheet, you'll find that this equation is right there, slightly rearranged. So if you had to guess what velocity this is, initial or final, what would you think? Yeah, initial. This is initial velocity. And our calculation is for a final velocity. If you rearrange this equation and put that VI in front, you have VF equals VI plus AT, which is equation number 4 on your graph, on your equation sheet on page 14. Okay? So having an initial velocity here is okay. Of course, we should have an initial velocity, and why is that? Well, let's take a look. When we looked at our paper strip, we had this horrible mass of dots here, and then we had some ever-increasing distances between our other dots. And the first measurement that we took was right here. And we measured that, and it was whatever it was. All right? But what about this tiny little bit here before the first set of dots? We don't know if that encompassed an entire tenth of a second, because when we let go of our bus, it could have been right at the tenth of a second, right when it was making a dot, or it could have made a dot and then we released it. But the bus was moving before it made that set of dots. We don't know if it was a full tenth of a second, so we have to discard that data. Okay? Because somewhere in there was the last set of dots, and we don't even know if we let go of the bus right when a dot was happening anyway. Right? So this little bit right here, the bus was moving, VI. That's that right there. Everybody get it? Okay. So I want to see this equation, all of it, written at the top. For your second bus, when you do your second bus, you can start here and say A equals, and then put in your equation and whatever it is, centimeters per second squared for your second bus, because your second bus will be on there. Find the color that works. Well, not having good luck with pens today. Still not having good luck. But anyway, let's say your second one here is in blue. We'll graph our second bus as well. Okay? So I want to see your slope calculations for both buses, your graphing for both buses. You should have some y-intercept that is probably not 0. And remember to get your slope from your line, not from data points on your line. All right? Once you draw those data points and draw a best fit line, your best fit line is now your data source. You can ignore the points that are on it. All right? Because each of those points is not necessarily representative of the whole. The line is representative of the whole. Okay? When you're finished, you'll take a landscape picture of both of these and submit it to me. You also have a little bit of writing to do underneath. That's on the next slide in Canvas. So if you go to the slide with the videos, click next. You've got the writing for the second one, just like you did for yesterday or Friday. And take a picture of basically just this and submit it. Make sure you've got your equations written on your graph where I can see it, or on the second graph where I can see it. That's it.